3 rivers and the rest of the streams. So this is the total populations, and we can also extract the population of streams here. Just we can see the population of streams here, but here is the total population. Then we find the objective function of these streams and these streams, because we already calculated the function of the sea and the rivers, and then we calculate the function value of the streams, and then sort the population from, for example, minimum to maximum, and then we proceed to this level. So in this case, it depends on the intensity of flow. Rivers and sea can absorb the streams. So that means if the river and stream, depends on the intensity of flow. For example, it is very clear that sea absorbs many streams to itself, because the intensity of flow in the sea is higher than rivers, and rivers also like that. So this is some one suggested equations. So we can designate streams to the rivers and sea. Number 1. This is 1 is for sea, and 2, 3, 4, for example, are for the rivers. So in this case, based on the objective function, we can, for example, we can designate the streams to the sea and rivers. After that, for example, I can say that after, for example, for 46 streams, 20 streams follow directly to the sea, because sea is very strong, because the intensity of flow in the sea is very high, so many streams follow to the sea. For example, 10 streams follow to river 1, 5 streams follow to river 2, for example, 3 streams follow to the river 3. I don't know the summation is 46, but I just give an example. So it's like that. This equation gives us like that. And after determining how many streams follow to the river and sea, so now the time is start for movement. The time is updating the position of the streams and also the rivers. In fact, streams flow to the rivers, streams follow to the sea, and also rivers follow to the sea. Sea is the fixed point, actually. Sea is the fixed point. So in this case, you can see that this is very simple equations. So we can see this kind of transfer equation, movement equation in many optimization methods. This is the kind of movement from one stream. This is the I is the current position, I plus 1 is the new positions, I is the position of the river, I stream is the position of the current position of the stream. In this case, we can update the position of streams towards the rivers, position of the stream toward the sea, position of the current river toward the sea, and then finally we have new position for the river. So this is a surface runoff model for the stream to river, river to the sea. Is a kind of indirect approach to the optimum point. So it is worth mentioning that the position of the sea, and then after the movement, we calculate the objective function of the stream. If the objective function of the new stream is better than river, the position of the stream and river exchange. And then again, if the position of the new river, which is the new stream, is better than the sea, the position of the sea and river is exchanged. So we have this kind of comparison after each objective function. So this kind of the position of the sea can be updated at each movement. So it is possible if we finally, for example, we have a stream with a very good solution. So in this case, this stream can be sea. After calculating the objective function, can be the sea. The new sea depends on the one iteration. After one iteration, we update the sea. So that updating for the sea it can be happen anytime, after any objective function. So after that, we go to the evaporation condition. For the evaporation condition, we assume that if the position of the river and sea is very close to each other, so this is the I think the first rule of the meteorology. The first rule, if you remember, in my first lecture, I mentioned about this. The first rule, we should avoid the collision. The collision is like this. If the distance between the sea and river is very small, smaller than Dmax, we determine the Dmax. Dmax is already a small number, but at each iteration, we also reduce the value of Dmax by iteration goes. But already Dmax is a very small value. The Dmax depends on your precision, how much accuracy you want. If the distance, a normal distance, if the Euclidean distance of sea and river is smaller than this value, then go for evaporation. Then evaporation condition is satisfied, and we have raining process. Raining process is like this: very simple equations. Local is a global search operators. then we randomly between lower bound and upper bound we generate new solutions for the for that river. So this is kind of if the for the sea and river, and if being between the sea and stream, because I told you rivers follow to the sea and also stream directly follow to the sea. Both happens. In this case, if the position of stream and sea is very close to each other, then again we have a evaporation condition is satisfied, and again we have a raining. And the new solution, the new position of the stream calculate based on these equations. That means for each stream we use this kind of global search operators to find new solution in the search space. So this is the schematic view of water cycle algorithms. We can see here the black circle. They are the current position of the streams. They move to the new positions here, and there are rivers. Rivers also move to the new positions, and here finally we have a sea. So in fact we have an indirect movement from the stream to the river, and river to the sea. And there's a possibility of movement of the streams directly to the sea, but we didn't plot in this figure. But we have three equations, updating equations from sea to river, river to sea, and also stream to the sea. So, as an analogy of water cycle algorithm in nature, you can see here in nature we have a precipitations. In water cycle algorithm we have an initial populations of streams. Streams are individual populations. In nature we have a stream. In a water cycle algorithm, individuals of population are called streams. And the best stream is sea, the second best is river 1, the third best is river 2, fourth stream is the third river, if I'm not mistaken. So rivers are second best solution, a number of best solutions. So if we have one river, in fact the second best solution would be river. Sea is the best solution, which is the best solution, best optimum point, and surface runoff is our moving strategy from stream to rivers and rivers to sea. And evaporation, we have evaporation condition, and one water cycle process is one iteration. And in fact, one iteration of water cycle is one water cycle process. This is some kind of analogy between the nature and water cycle algorithm, which we are inspired from the nature. So this is the flowchart of water cycle algorithms. So actually the fonts are very small. So but you can find it in the published paper in 2012. Here is the pseudocode of the water cycle process. So I will go through to the codes and then show you in MATLAB so how to work with lines, how we can run the and one. I will give you an example for constraint optimization problem and also unconstrained optimization problems. So maybe this is in your mind. So how we can handle a constraint for the water cycle algorithm? In fact, we developed the water cycle algorithm for constraint optimization method. So for the constraint handling strategy, we use simple rules reported by the DEP in 2001, and you can find it in literatures. The four simple rules are like this: any feasible solutions are better than infeasible solution. That is for sure. I mean, if I want to, for example, select one individual in my population as the C, for sure that solution should be feasible. For sure that solution should be feasible. Rule number 2. Infeasible solutions with violations around 0.01 to 0.001, we can consider them as feasible solutions. So this is another rule. So infeasible solution with this kind of constraint violations are considered as feasible solution. The third rule is a feasible solution with better cost, with better objective function, for example, for sure, are better than feasible solution with good cost. So this is very clear, in fact. So feasible solution with lower cost, better than feasible solution with low cost. And last but not least, if you have, for example, you generate your populations in lower bound and upper bound, but unfortunately, because you are not very lucky sometimes, all the individuals in populations are infeasible. In this case, what should we do? In this case, okay, no problem. That infeasible solution with smaller violation is better than other infeasible solutions with small violations. So in fact, you should select the best solution as the C, and the rest as the stream and rivers. So in that case, you go for that infeasible solution with smaller violation constraint, with smaller constraint violations, and then you go ahead, and after iteration goes, the solutions comes to the feasible region, and then all your populations after some iterations would be in the feasible region. So you should not worry about that. We can see here in case. So I hope you can find out what are those 4 simple rules. If you go to this paper, so you can they are mentioned about these rules, and then solve some problems, and then show the efficiency of this kind of constraint handling over the penalty function, because you can use also penalty functions. It's not a big deal, but penalty function also has lots of details, like static penalty function, dynamic penalty functions. So this is not it's not like that you add 1 million to your cost function and then you penalty to your algorithms. That it can be like this, but it's a very simple one. But comparing to the penalty function, I think based on my experience, this constraint handling approach works very well. So you may use this one in your codings not for WCA, for any optimization method you use. You can use this kind of constraint handling approach. So this is the first paper published in 2012. I did it in my PhD program when I was in Malaysia as a PhD candidate, and then in 2016 we in an open access journal we published the source code of the water cycle algorithms in Software X, and it's open access, and you can freely download the paper from the website. And so how about checking the WCA code in MATLAB if you have
Ali,
the codes are on my website.
Dr. Ali, can you hear me?
Yes.
Yeah, actually,
yes.
We got a question. Before going on to MATLAB, we can actually take that question. Mr. Prabhujit
Yes, sure.
Mahapatra, he has asked how the diversity is maintained in WCA.
A very good question. So the diversity in the WCA mostly refers to the evaporation condition. As you can see, we have a very good, a very famous and a very well-used equations. I mean, I can go back to the slide. This equation can be, this condition and these equations, form the global search of the WCA at the first site. At the first site, this condition and these equations form the global search of WCA. But as you know that when we usually run the algorithms, the first populations, usually the diversity between the population, between the individuals are very high. At the first iterations, the standard deviation of individuals in the population is very high. So in this case, we have also global search at first iteration using the movement strategy. At the first iteration, these equations also work as global search, but for sure at final iterations or after, in the mid iterations, these equations work as exploitation operators, and this area, this section refers to the exploration phase of water cycle algorithm. I hope I could address the comments.
Yes, I hope it addresses. You can move further.
Okay. So let's see. Start with the MATLAB. So I should exit, and no, I can just like this, and then open the MATLAB. So I can. I want to make sure you can see this one. Yes. So I go to the WCA unconstrained. So this is the code, which you can find it also in the website. So this is the function code. There are some input and some outputs. So this is the name of the code. This is the input. So the input is first, what is the objective function? What is the lower bound? What is the upper bound? How many design variables do you have? What is your population size? What is the number of sea and rivers? What is the value of Tmax? And what is the value of maximum iterations? So this is the input of the code, and the output gives you This is your design variables. This is the cost function. I mean the cost function value. This is your minimum value, and this is the number of function evaluation used, and this is your elapsed time based on the second. So very easy. Just let's go through the code. I think maybe you're interested to, because you may download the code, but it's a good time to go through the code and see how it works. So in this case, I made some default here. For example, if you don't choose the number of populations, and if the number of population is empty, just default put it 50. If the NSR is empty, just default put it 4. If the Dmax is empty, just default is this value. If the maximum iteration is empty, just default use the 1000 iteration, something like that. But you can here, like here I mentioned here, you can use this value and define everything here. It's up to you. But in case if you don't put any value here, I mean until here you need to put the values, the input values. But if you don't want to put this value, the WCA works as default. So after defining the input parameters, so we start the clock at tick. We find the number of streams, number of population minus NSR, and then we how can I say, we can form the initial population as very randomly between lower bound and upper bound, between the lower bound and upper bound. For each individual, this is the loop. For number of population for each individual, just saving the position. We use the structure in MATLAB. We use the dot structure. Very easy for coding, actually. I suggest you code your codes with this strategy. It's very easy and understandable. So the position in the pop and the cost in the pop. In this case, you can form all the populations, position and cost in the pop. Okay. For example, if I want to see here, if I go here, and then step in and then come here, for example, here, we can see that pop one is like this. I already mentioned the number of design variable 100, so it's very high actually here, we cannot see here, and the cost value is like this. So population pop one has the position is like this, and the cost is like this. Actually, the cost function is sphere function. A sphere function is, the sphere function, x1 power to 2 plus x2 power to 2 plus x3 power to 2, like, and so forth. Here, the number of dimension is 100, so it's a big dimension actually. But the function is very simple. We know the optimum global point is 0, and all the position should be 0 as well. So, for example, if I say that pop1 dot position, you can see that this is the position of the pop1. It's 100 dimensions. So something like that. After that, we create so we can do this for 50 populations. We can do it for 50 populations, and this is 1, and then we can go for 2. This is I2, and then population is 50. Now we have population 2, and so forth. So after that, in here we have all our 50 population here. So for example, CLC, what is the pop? Pop is a structure, 50 times 1 cost. So any position you can find. For example, pipe 13. So pipe 13 is like this. The cost is this. The position is like this. So and then we go forward. Then we sort the population based on the cost from mean to max. So in this case, this is the index. For example, individual number 14 has the minimum cost, so it should be the C. It should be the C. Then the C is population number 34. So as you can see, the cost is 2,413. So this is the C for sure. And then after that, so in case index number 10, index number 26, index number 29 should be the reverse. First river, second river, and third river. So here we do this. NSR is 4, 4 minus 1 is 3. So in this case, 3 index after C. I mean 1 plus 1. This 1 is related to the C, so that's why I mentioned, I put the 1 here, because already we used the 1, which was 34. So in this case, the 4 digit after the 34 are considered as index for river. In this case, we have river 1, river 2, river 3. So we have 3 river. So if I see here, river 1 is like this. River 1, river 2, river 3. And river 1 already has position and already has a cost. And then about the stream, so the next, the rest of the individual or streams, that means after 4 plus I started from 1 to 46. All are considered as streams like this. If I go here, we can see the streams that the 46 times 1 structures has a position and cost. For example, the stream, for example, 23 is like this. The cost is like this and the position is like this. So if I decrease the dimension size, would be better. For example, that we could start with dimension maybe 5. Let me run again with dimension 5, then you can see it better. Until here. So for example, C is like this. We have 5 dimension here between lower bound and upper bound randomly, and the cost is 56. River 1 is like this. For example, river 3 is like this. Stream like 8 is like this. So now we have our sea, our rivers and stream. Then we go to design the streams to the rivers and sea. So that equation I already showed you in this slide. So in this case, there are some coding techniques and coding skills. You should do this. Otherwise, you may get errors during the optimizations. Depends on the problem. So at first, we sort all the costs in one CS, and then in case sometimes we have a duplicate solutions because because the accuracy of the solution is very close, and suddenly you may have a duplicate solutions or the same solution. In this case, you may have an error. So this is the same equation I already showed you in the slide. The round of absolute Cn divided by summation of Cn. I can show you here. This is the same equations. This equation is like that one. Ns. Cn divided by the summation of the Cn times n number of streams. And then in this case, so we can find out, for example, here I come here, then maybe we have so in this case, yes, because the dimension size is like that. So here we mentioned that 19 streams go to the sea, 15 streams go to the river 1, 8 streams go to the river number 2, 4 streams go to the river number 3. Okay, so we have 1 sea and 3 rivers, and that's okay. And then finally we remove the 0 in the next lines. So in this case, everything is right. 19 streams directly follow into the sea, 15 streams move to the river 1, 8 streams move to the river 3, river 2, and 4 streams move to river 3. And then here we remove the 0 here because we mentioned that the end ns should be equal to nothing. So in this case, we can see ns is like this. And then we sort ns is already sorted, but we use this. So we already defined the number of streams to the sea and rivers. That's all. Here is like modification of number of ns, because sometimes it may happen. Sometimes there is a difference between the cost function of sea and the cost function of the river. In this case, the sea absorbs the major amount of the streams, and sometimes for the for the last river there is no stream to absorb. In this case, we get the error from the codes. These equations from here to here, I modify the number of C, the number of the NS, because if all the rivers should have some rivers, the minimum is 1, something like that. These codes check the NS in case if, for example, the number of streams moves to the river 4 is 0. Then what we do, we reduce from the 19 and add to the number and add to the last value. In this case, we modify the NS. For example, if find the value of NS equal to 0, so there is no NS equal to 0, so that's all, no problem. So we can, here we don't have any problem, just jump, because our NS is correct. So there is no NS equal to 0, because sometimes one of the variable, these kind of numbers maybe can be 0, depends on the problem. In this case, you may get an error from the codes. So we made this to to modify the NS for solving the problem. So here there's no error because we already have the NS is correct. So here we we changed the order of NS to from the 19 to 4 from the descent, from minimum to maximum, or maximum to minimum, descent, not ascent, from the descent. Here also we use the same, it's kind of repetitive lines here. We already do this. Oh, this one we did this because sometimes based on this modification, this order may change. That's why we put it here to make sure about the order. That's the reason. Yeah, that's the reason. Because I developed this code in 2016, like 4 years ago, 5 years ago maybe. So in this case, sometimes I forget what I did before. So then, I hope this would be not boring for you. I hope so. Is there any comment or feedback? Just let me know, and then I will just, skip or just goes fast.
It's fine, Dr.
And then
Ali.
after,
The way you want, you can
it's good.
proceed.
Okay. Okay. So then from the NS, we should separate the sea and rivers. I did this here. NS is 19, 15, 8, 4. I just want 19 here. NAB, okay, NAB is just for rivers. NS1 is just for sea. NS parenthesis 1, that means 19 stream to the sea. NAB is just only for rivers. I just divided river and sea. I just divided because our movement is independent to each other. So I divided rivers divide, NS divide. NS is for the sea and NB is for the river. So here the main loop of the water cycle we can see here. So for the first, we started from moving stream to the sea. Okay, moving stream to the sea is like this. The position of the new position of the stream is like that. The current position plus 2 times this rand and sea position minus stream position. This one is, as you can see here, yeah, this one. The stream to the sea, this one. The stream to the sea is like that. We mentioned the exact equation here. So it's like that, and then we check the new position is between minimum and maximum, between the lower bound and upper bound, because sometimes based on the movement we may violate the lower bound and upper bound. So here we check, make sure this new stream, the new location, the new position of the stream is between the upper bound and lower bound. This is to make sure. And after that we find the cost function. The cost function is like this. This is the input. Because the cost function is sphere function, the x comes here, and then find the value of the cost function, and then this is the cost function. Then we compare this stream with the sea. If the cost function of the stream is lower than the sea, just the new stream is the sea, and the sea is the previous stream. I change the position. So we did this like this. First, I save the stream, this very valuable stream, in this parameter, and then I designated the C to the stream GA, and now the previous stream is C, and then the new C is the C, because if you mention C is the stream, you already remove the stream in your code. So in this case, you should first put this one to one new parameter, and then you already have your new stream here. Then after defining the C to the stream, you change the value of the C, something like that. So this is the moving stream to the sea, and moving stream to the river is like that, same as that. But here you should be careful. You should be careful because you should work with the NB. So that means that this loop should be repeat for 3 times. Is it right? 3 times. 4 minus 1, and for each time it should go for how many times? 15 times. For example, for river 1, how many times? 8 times for river 2, 4 times for river 3. So this is the same. This equation is the same with this stream to the river, but because of the indices, so it's a bit long, but it's not very terrifying. So it's very easy actually. You should be careful. You always should. This J should be always plus this value, because we should obey the orders of the total populations. Otherwise, the numbering would be very hard to find out which stream follow to which stream, which river. You should be very careful about this. And then when when you updated the position of the new streams, you just check between lower bound and upper bound, and then you find the cost function here. This is the input data. Then this is the cost function, and if this stream is smaller than your cost, your river, and if the value of the stream is smaller than the value of the river, just change the position of the stream and river, and then again check if that new river, which is the new stream, is smaller than C, then also update the C. We have two updating here actually. One is stream and river, and then maybe that new stream is even better than C. It may happen. Maybe that new stream is maybe better than river, so better than the C. So just check that cost with the C cost. If that cost is smaller than the C cost, then also the river and C change the position. And also we have a moving river to the C. Same. This equations river to the C, and then check that new position is between the lower bound and upper bound, calculate the cost function, and then check the cost function with the C cost. If this cost is smaller than this cost, just change the position of river with the C and C with the river, something like that. Then check the evaporation condition. If we have, as I mentioned, we have two evaporation conditions for the sea and river, for the sea and streams. For the sea and river, this is sea and river, yes, river and sea. This doesn't matter because this is the absolute value. So if the norm distance of river and sea is smaller than Dmax, with this probability, this is based on the experiment, 10% mutations. Then do the evaporation condition is satisfied, and the new streams randomly generate between the upper bound and lower bound. How many times? This 3 times, 3 loops. How many times this loops works? 3 times, like 1, 2, 3, because we have 3 rivers, and then find the position of the rivers with the C. If this is smaller than this value or this possibility happen, then we have a new streams based on the rivers. And then also check the evaporation condition for the streams towards the sea. The streams here, how many times? 19 times here, because NAS1 is 19. For 19 times, check the position of each streams with the C. If it's smaller than the max, then just find or obtain the position of the new stream based on the global search operators. And then iteratively, at that iteration, decrease the value of Dmax by this equation. Maximum iteration is 500. Dmax is we set as 1 e minus 1 e minus to power minus 16, and then Dmax reduce, and then display the iteration and then the cost, and save all the best cost in the at each iterations here, and then the talk, the time, plotting, labeling, and calculating the number of function evaluation. That means at each iterations we have 50 population size. That means we have at each iterations 50 function evaluation. That means 500 times 50. That means the total number of function evaluation you use in your algorithms. And then finally, x mean is the C position, and find f mean is the cost function of the x mean. So if like this, I think run the algorithm. So you can see for 5 dimensions, this is the function f mean, and the iteration you can see here. So, and this is the convergence figure of the reduction history, the function value versus the number of iterations. So let me increase the number of this to 100, and then 50 number of population, number of NSRS. This is like, for example, 1000, and this is minus, this value is good. This is the default values. You can use this value for your, actually the WCA is not very sensitive to Dmax, because Dmax is already a small value, so it's not a very big deal. Usually it's not a very big deal. So for 100 dimension, this is the cost, and this is the location of the optimum solution. You can see should be 0. The optimum goal is the 0, 0, 0. And this is the elapsed time, 7 seconds, and the number of function evaluation is 50,000 function evaluation. So this is the application of standard water cycle algorithm for the small problem, sphere problem, and this is not shifted, this is not rotated, this is not hybrid, very small objective functions. Not small, simple one. This simple one in terms of the complexity. Uh, so I mentioned here global n-vars. What's the reason of this? I already defined an n-vars number of variables here, but here I need the n-vars. So I can say that n-vars is okay 100, no problem. But in case when you change the value here, for example 30, you should come here and then change here to 30. So what's the point? If I use this format, these equations, I mean this command, yeah, it's better to say command. This command, if you global n-vars, here you can just mention global n-vars. Then in case if you change every values here, for example 60, no need to change here, because this one n-vars is not correct, because it already here you already globally define this parameter. So you should not be worried about the changing this value. So whenever it's 60, here is also 60 as well. No worry, just run. That's why I use the global n-vars here. So I think everything is clear. I mean, I think maybe many of you knows about this kind of details.
Dr. Ali.
So yes.
We got
Yes.
We got a few questions. I think we can take them at this time. It will be better.
Yeah.
Mr. Malleswar Rao, can you hear me? You can unmute your mic. Probably he is not there, but he has asked a question, so I can narrate his question. His question is, if we want to design a multi-objective hybrid algorithm using WCA in combination with another one, which algorithm is more suitable to multi-objective WCA? Means he wanted to have hybrid of WCA for multi-objective. So what is the preferable another algorithm?
Actually, it's a kind of very hard question to answer, because usually when we hybridize, when we improve the algorithm, when we even develop a new algorithms, in fact, we don't know about the performance of the algorithm until we can see in the examination. When we can see the performance in practical, then we can say that, okay, this algorithm is better than this algorithm, based on some statistical tests and statistical result. In this case, telling, for example, okay, hybridization of WCA with TLBO in multi-objective would be a good algorithms. I cannot guarantee, actually. Maybe the result is good, maybe the result is neutral, I mean, same result, or maybe you can improve the result. And sometimes after hybridization or after improvement, you can see that even the original algorithm is performed better than the improved version. It happened to me. I tried to improve one algorithm, and suddenly in practice, I see that, okay, the result of the original one is better than my improved version. So what's the point of improving the algorithm? So maybe my improvement strategies was not very well, something like that. So I cannot say any specific algorithms, for example, just go for WCA and, for example, TLBO. But in case, I can change the question like this. What kind of algorithm is better to hybridize with water cycle algorithms in order to get better result? We can see that, we should know that, what are the advantage and disadvantage water cycle algorithm. I can say that water cycle algorithm is somehow weak in global search. As you can see, the global search operator is very simple one, and we just use the uniform search or random search. So in case, if you can use the lady flight strategy, for example, if you can add some algorithms with very great potential in global search, combination with water cycle algorithms, maybe overcome or maybe compensate the disadvantage of water cycle algorithm, and then the overall performance would be good, something like that. So then you can see what are the algorithms with good explorations. So maybe GA, maybe Harmony search. Those are good exploration algorithms, or maybe other algorithms. So in this case, algorithms with good exploration capability are the best for hybridization, for multi-objective for sure. So in this case, my question would be like that. My answer would be like that for that question.
Okay, Ali, Dr. Ali, that makes sense. Dr. Jatinder Kaur, are you there? You can unmute and you can ask a question. so probably she's not listening me. She has asked.
Hello?
Yeah, yes, ma'am.
Hello?
Please proceed.
Yeah.
Dr. Ali is listening you.
Sir, yeah, sir, my question is, do we have source code in any other language for WLC, WCS?
Yes, you can find the source code in the website, my personal website. I mentioned at the first of the presentation. So then you can find the standard code, the constraint version, the multi-objective version. So no problem.
She's asking, is there the code is available in any another language other than MATLAB?
Wow. I see. I saw some of the scholars in MathWorks. They mentioned that they put the C++ version of the code, but I just saw it, but I didn't use the C++ code. If you search for the other versions, you can find it. There are in the literature, yes. In the
Okay,
GitHub.
only in C++.
Pardon?
Only in C++.
Yeah, I saw the C++ version, but maybe you can find in Python. So I didn't search actually because I'm a kind of MATLAB person, MATLAB guy, so I was not interested with other language. But I know there are many other types of the version of water cycle algorithm. But sometimes, the others, they don't share the codes. I don't know why. So maybe you can send an email to them and ask for example, WCA in Python, WCA in C++. So maybe you can ask them to give you the code. But my plan is like to also include the other version of the programming languages in my website. But so far I didn't do that. But I will promise to put the other versions of the code also in my website. Then it would be easy for you. But I heard that there are some conversion software. For example, it converts from C++ to MATLAB or vice versa. So, but I heard that still you should have to do some modifications to run the codes. But in case if you are master in C++, if you convert from MATLAB to C++, then you can find out the bugs and debug the codes very easily. I mean, it would not be a kind of big deal. I think so.
I think Dr. Kaur has got her answer. Nahid Fatima had the same question, so probably if she is listening, she had her answer. Dr. Divya Pandey, if you are there, you can ask your question. So I'm asking on her behalf because she has already pasted her question. She's asking which optimization techniques are more suitable for multi-objective hybrid systems having real life application in present scenario.
Okay. I don't want to be a biased person, but NSJ2 I think is a good choice, but still we cannot guarantee finding the better solution using the NSJ2. But usually NSJ2 I saw in many papers for the wide range of problems, the performance of NSJ2 is a good one, but it's not a guarantee. Even multi-objective water cycle algorithm can perform better because even in our papers, in benchmark multi-objective optimization problems, we surpassed the NSJ2. But you are free to use MOWCA, NSJ2, MODE, multi-objective differential evolutions. So this kind of algorithm you can use, but I mentioned that we cannot say that which algorithm is better than which algorithm until we see it in practice. We can have some guess or some assumption, but sometimes we are not always right. So my suggestion is just go for coding the NSJ2, or you can find the codes in websites, and also you can find my code in website. Just apply it, and then because as long as you don't want to code, so you can have your time. Just you don't waste your time. Just it's kind of applications. It doesn't take your time too much to check the performance of several algorithms.
Yeah, that's sure. That makes sense. Dr. Varnika Agrawal, if you are there, you can ask a question.
Yeah, good evening, sir. I wanted to ask if you can discuss the application of WCA in traveling salesman problem.
For which kind of problem?
The traveling salesman problem, TSP problem.
Yes, yes. It's a good question. In 2018, we published the application of discrete water cycle algorithm (DWC) for TSP problem. So I don't have. I already have the paper here, so you can find it. I think here. So you can find it in this paper. So there are the performance and application of water cycle for TSP problem here. The last, I think the last one, this paper, can you see? The discrete water cycle algorithm for solving the symmetric and asymmetric traveling salesman problem. So in this case, you can find the application of water cycle for TSP.
Okay, thank you so much, sir.
You're welcome.
Another question we have from Professor Kusumdeep. Ma'am, are you there, or shall I narrate your question on behalf of you?
Yeah, I'm there.
Yeah, ma'am. Please.
First of all, let me congratulate you, Dr. Ali, for an excellent presentation.
Yeah.
My simple question is about the performance of your algorithm. You see, usually we have standard benchmark test functions on which we evaluate the performance of any meta-heuristic algorithm. So I wanted to know, have you investigated the performance of your algorithm on such kind of a benchmark, standard benchmark set, for example, the IEEE CEC benchmark set, or any other such benchmark set?
Yeah, thank you very much. It's a very good question. Yes, I didn't mention about the paper. I think so, but yes, we have some papers. We tried with the CEC 2015, like IEEE. Yes, it's IEEE actually. CEC is belong to the IEEE, if I'm not mistaken.
That's right.
But for 2015, we tried the performance of the algorithms. But that was the only case. We didn't go for 2017, 18 because every year they provide some benchmarks. Once we published for 2015, yes.
That should be fine. Once you have done it for 15, then it should be fine. Yeah.
Yeah, I'm looking for the, just.
Yeah. And another similar question in the same lines is about the comparison with the other existing algorithms. Do you compare with the, let us say, the PSO or the anti-colony or some other kind of algorithms of this category?
What is the I didn't notice about your question very well.
No, I'm asking the comparison of your algorithm, WCA, with the PSO or DE, etc. Did you make some comparison?
Yes, actually, I already had some slides about the comparison between WCA PSO, but in some of our papers we prepare, because the reviewer usually, because as I know that you are a very expert reviewer for many prestige journals, so this kind of question usually reviewer ask at the first initial stage of the WCA. They ask what are the difference between PSO and ACO, WCA, ACO, WCA, and some water-based algorithms. So because in the literature there are some water-based optimization algorithms based on the water. So they ask this, and then in the review we revise our manuscript and showing the differences between the PSO and WCA in the tables. But I don't know which one of my papers. So I can find it in my papers, and then there's a table. So for example, this is the problem. This is the strategy in PSO. This is the strategy in WCA. The differences and the similarities also. Sometimes we have an overlap. Actually, I think many optimization algorithms, they have some overlap, but then these overlap should not be very marginal. It should not be very severe. I can say that. Overlap is for sure for most of the optimization methods. This is it for sure.
Right. Thank you so much. Thanks.
You're welcome. You're welcome, ma'am. Thank you.
Okay.
Thank you, ma'am. Mr. Prabhujit, are you there?
Yes, I'm there.
Please go ahead with your question.
Yeah, so thing is that, so can we connect the streams of different rivers? Like one stream will be connected to another stream of another river. Streams can be connected of different rivers. Like streams is connected to river, streams are connected to seas. Okay. So stream is updating towards the river, stream is updating towards the sea. So one stream can be updated to another better stream also, na? That is also possible for better convergence.
Could you repeat the last part of your question? The last part.
Stream of one river can be updated towards the stream of another river. They may
Okay. Yeah, very good, nice, very good question. Yes, that is possible. That is possible, but in standard water cycle algorithm, it does not like this. So it can be kind of improved version of water cycle algorithms, like fully informed.
The convergence speed. It will improve the convergence speed.
Yeah, that's right. It may improve the convergence rate. Like PSO, fully informed PSO, in the fully informed, we have a, for example, in the case of PSO, we have a FI PSO, fully informed PSO. In the fully informed PSO, the individuals, just like, in the standard PSO, we just randomly walk, and then we just look at our personal best idea and global best idea. But in the fully informed PSO, you can also look at other best personal idea. So in this case, they call it fully informed PSO. In case of WCA, we can go for fully informed water cycle algorithms, like streams also have some look to the other rivers, in addition of their own rivers, something like that. It can be possible.
And another thing, up to what dimension WC is capable in solving the problems? Up to what dimension?
I mean, up to my dimensions, the finally was like 1,000 dimension. I think I myself applied the water cycle, like 415, 400, 500, yes. But for the benchmark, I increased the number of dimensions, but I didn't report in the papers, because usually the papers, like for the benchmark, like 100, 200, 500 is enough. 1,000 makes the manuscript very lengthy. But I didn't see, I didn't check to 10,000, 1,100. But in case when you increase the number of dimensions, you should also increase the number of function evaluations. It's not like you have 10,000 dimensions for 1,000 iterations. It's not possible.
Yeah,
it's not possible.
You converted the WCA to multi-objective problems also, multi-objective version of the WCA. So how you have done? Using the non-dominated sorting, or what concept you have used?
Yes, exactly, non-dominant sorting. It in fact is NSWCA. Yes.
Yeah.
Non-dominant sorting is sorting.
Thank you.
Very well, very good.
So for the time being, we don't have more questions. So you can conclude your presentation and proceed.
Okay. So I already prepared the constraint version here. In the constraint version, so we have function. I chose the speed reducer problem. You may know about this problem. It's a benchmark engineering problem, speed reducer problem. I know most of you know about this problem, and this is the function value. This is the mathematical function. This is the constraint of the here. This is the constraint of the speed reducer. We have a constraint 1, constraint 2, constraint 3, 4, 5, 6, maybe 12, 11 constraint, and we have a function, and we have a main code for run, and we have a WCA constraint version. So for WCA constraint version, in addition to objective function, we have a constraint here. We have a constraint here. Oh, sorry. We have a constraint here, and we have a function, objective function, and the rest are the same. And then at the default, for constraint problems, I suggested to use this value for the constraint version. Dmax should be a bit larger than the unconstrained one, because in the constraint version, so we need to sometimes satisfy the constraint violations. So in this case, we should have sometimes flexibility for algorithms to move. So this value usually gives some accuracy to algorithms. So I mentioned here, for unconstrained problem, Dmax should be in, and for constraint problem, Dmax should be like this. This is a suggested value, but you can also use with -16, but based on the experience, these values are better in solving problem. So the strategy is almost same here, but here we should calculate the constraint of that individual. The constraint like that, this population size, this individual goes to the constraint here as the input, and the output is C. So let me check. So here we have 7 dimensions, 7 design variables. This is the lower bound and upper bound, and we come here, run, step in, okay, until here. So we have population 1, and then this is the value of this individual shows that only 2 constraints are not satisfied, because always we should have minus value, yes, because the standard format of the minimizer of the constraint optimization problem is gx smaller equal and smaller than 0. So all value smaller than 0 are the best. I mean, we are in the feasible region, but if we have a positive value, that means we are in infeasible region. So in this case, this individual pop1, which is pop1 here, if I mention pop1, so the cost is this, it's a very big one, and this is the position value, and this is the constraint violation. So this is a summation of the constraint violation. That means that 0.13 plus 0.15, that is 0.29. This is the summation of the constraint. So we work with the summation of the constraint violations. We care about one value. This is the summation of the constraint violations. You know what I mean? So if we reduce this value to 0 or minus, then we are safe. We are in the feasible region. So that's the thing. So here we calculate the cost, then we sum all the positive values. Positive value. This is very small positive value. We find the summation of the all positive values, and then put it as a constraint violation for that individual. And then it can be repeated for the population 2. Let's see for the individual 2 what happened. The cost is still we are in the infeasible region, and vice versa, and then so forth. For example, if we come here, we can see here pop, for example 10. Sorry, pop 10. So still we have a constraint violations 0.7p. So it's a high one. So let's see. Here we do the how can I say, we separate the minus and positive values. I want to separate the minus value and positive value. The minus value, that means the constraint with minus value. So the constraint with minus value are the best. So I put it here. The constraint with positive value are here. So if I want to go through the code, it takes time. So let me show you what happened here. So in this case, we have x minus. That means this is empty. That means all the individuals have the constraint violations. That is 50 now, because here is minus, is 0. That means all the individuals are in the infeasible region. So it's a very bad lucky. So our first initial population is in the infeasible region, unfortunately. So it's okay. We should not worry about it. In the first situation, we can move to the feasible region. So here is x minus. That means we don't have any minus constraint. I mean, every population has the positive constraint, summation of constraint. So, okay, this is the situation that we have infeasible solutions, and infeasible solution with smaller violation is better than infeasible solution with small violations. So then C is pop1. Pop1 with the smaller violation, which is 0.13. If you sort this is already sorted. Actually, we already sort this. Sort based on the index. So x plus is already sorted. Here is already sorted. You can see here, sorted, already sorted. So x plus, the first one is the least constraint, has the least constraint violation, which is how many? Which is 0.13. So this is our C, and the second, third, and fourth are the reverse. And this is the reverse. For example, river 1 is like this, 0.16. So and so forth, and this is for streams, and then we find how many streams follow to the sea, and how many streams follow to the rivers. Here is almost the same, no difference until here. Actually, all the same until here. Okay, well, let me see until here. We can see that in NAS is like 18 to this 18 streams follow to the sea, 15 streams follow to the river 1, 12 streams follow to the river 2, and one stream follow to the river 4. This is happened because before this one was 0, and we modified the code to have a one river, one stream here. That's why we have a 1 here. So something like that. So again, we have a movement of the streams follow to the river sea, and then check the lower bound, upper bound, and the objective function. Okay, here is very important. So when we find the objective function, we should calculate also the constraint of the new river, the new stream. So still we are in the infeasible region. So calculate first the summation of the stream. The summation of the stream is now 14, for example. Do you remember the summation of the sea was 0.13? So this stream for sure is not better than the sea, because the constraint violation is higher than C. So for sure, even the objective function is this. Even the objective function is lower than C, but we don't care, because this is important. The constraint violation is important, and first we should try to reduce this value at first. Then we should think about the function value. So in the constraint problem, first our constraint should be constraint satisfaction. After the constraint satisfaction, then we think about the function value to reduce the function value. So it's like the strategy is like this. Because, for example, if you find a very, very low function value, but with a high constraint violation, you should throw away the solution. But if you have a solution with very high function value, but already in the feasible region, that solution is more valuable than the another solution. I hope you get the point. So in this case, we compare the constraint violations with the stream. So here I mentioned the three rules here. So if, for example, the C constraint, the summation of the C constraint is smaller than, that means that if, for example, we are in the feasible region, and then also the constraint violation of the stream is feasible, and the cost of the stream is lower than the cost of the C, then do this. Then change the position. Or if we are in the infeasible region, that means the C but the stream constraint is negative, that means, for example, in a kind of case happens, your streams already is in the feasible solution. Then in this case also you can change the position of the sea and river. And another situation, if the constraint violation of the sea is positive, that means the sea is in the infeasible region, and also the stream is also in the infeasible region. Both are in the infeasible region. See, the constraint violation is positive, but the sea constraint violation is, or I can say that the stream constraint violation is smaller than the sea constraint violation. In this case, the stream is a good point, better than the sea. The stream is better than the sea. So then change the position. So it would be good if you could record the lecture, then later they can re-listen to the lecture to get the point.
I think, Dr. Ali, we forgot to start recording this. So next, from tomorrow onwards, we will remember to record the lecture.
Actually, I have did recording, but it's not from the start point. It's from in between. So we have the recordings, but not the full.
Okay.
I mean, coding is important. I mean, even for the code part, it would be enough, I think. It's okay. Because for the slide, they can read the slides. I think everything is clear. But in the coding part, I mean, here they should have more attention. And maybe it is necessary to double listen to the videos. It would be better. So in this case, also the same situation happens. River follow to the stream. Stream follow to the rivers. Calculate the objective function. Check the okay, if you want to use this kind of a strategy for handling the constraint, you can use this kind of code for every optimization method you want. For TLBO, for DE, for spider, for any optimization is in your mind, you can use this kind of code to handle the constraint. So it is not only for WCA. It can be for any optimization method. And there are some trick here, so it takes time to go through exactly. So, and then also for the C, for moving the rivers to the C, then here we check if the C is in the feasible region, and river also is in the feasible region. If the cost of the river is smaller than the C, just change. Or if C is in the infeasible region, and river also, and river is in feasible region, C is different. If C is in feasible region, but river is in feasible region, then again change. And another thing, if C is in infeasible region, also river is also in infeasible region, but the constraint valuation of river is smaller than the constraint valuation of the C, then change the river and C, because we are looking for the best point with the minimum constraint valuation and minimum cost. So this is the strategy. And the same for the, evaporation conditions, and reduce the value of Dmax. And then finally, you can see, let me check, we can run here. You can see that the summation of constraint is 0. Summation of constraint is 0. I think of 1000 iteration, I think. So the summation of constraint violation is this one. This is the minimum function value, average. So this is not problem. Yeah, the summation constraint is 0, exactly 0. So let me see at the first iterations. At the first iteration, I think we have some, no. So even you can see that even at the first iterations, after the first iteration, the summation of constraint is 0. That means after the movement, we could find the feasible solutions. That's why in the final, at the final of the iteration 1, we cannot see any constraint violations. So let me, I can also start with, no, I cannot change it because this should be the same. Here, we cannot increase the number of design variables because it's not a benchmark. It's a kind of real life problems, real life engineering problems. So I cannot change the design variables, because if I change, I should add here some lower bound and upper bound, and I should change the constraint. So it's very hard. So it's okay. It's kind of, and these codes are in the website. You can go and then check for example, for 3-bar truss, for pressure vessel problem, for spring design, welded beam design. Just comment, uncomment, and then here just comment, uncomment. Then just run. That's all. I think for the coding, it is enough. I mean, for the constraint and unconstrained versions. So how about moving forward? So if there's any question, also I can answer the questions. So this is the codes also available in the website. Here you can go to the ali-sadullah.com under the download. Under water cycle algorithm. Here you can click, and then you can find the codes for standard, constraint, multi-objective, discrete version, something like that. You can find it. Here's the
yeah, Dr. Ali, sorry to interrupt you. If we have questions, then it can be typed in the chat box, and then I can organize and I can ask to Dr. Ali, because he is available with us. Else we'll move forward to the end of this first lecture.
Okay. So I mean, we don't have time, you mean?
You can summarize. You can take next 5 to 6 minutes more, because the scheduled time was by 5:45. We have already crossed that. So you can summarize, and for the time being, we don't have any questions.
Okay. So I just want to briefly go for the review part. I mean, this is a review of the water cycle algorithm we just recently published in the neural computing applications. The neural computing with applications, a comprehensive review of WCA. It's around 100 pages in one column. So just we got acceptance, and it will be online soon. So this kind of number of papers based on the well-known algorithm in the literatures, until April, I think, if I'm not mistaken. Then this is the number of published papers regarding to the WCA in different journals: Elsevier, Springer, IEEE, Taylor's, Hindawi, and other journals. And this is the kind of circular plot of that journals. Like we can see that 30% of the papers published in Springer, 28% published in Elsevier, and this is based on the per year. We can see in the first year, it was only one paper by me in 2012, and then in 2019, I think had the highest rank, 28% of the papers published in this year, and 22 in 2020 is like 11% so far. And this is a kind of water-based meteorologic optimization algorithm. Like I don't know some of the name of these algorithms, like water wave optimizations, if I'm not mistaken, radial flow optimization, something like that. High logic, I don't know the name. So those are based on the waters actually for the continuous and discrete problems. So we had some like comparison between these kind of algorithms. We can see here what is the initial population in RFD drops, in IBD the water drops, something like that. In water cycle algorithms, here are streams. So then the year of proposal, the citation so far, and this is the differences between the these kind of water-based algorithms. And this is the number of citations so far they got from the Web of Science. So among the water-based optimization algorithms, WCA had the highest ranking. After that, IWD has the second rank, and the water wave optimization the third rank. And this is 41% regarding to WCA among the water-based optimization algorithms. And this is a modification of water cycle based on the chaotic, fuzzy logic, binary, discrete. This is the DWC, discrete water cycle algorithm for the TSP problem I mentioned. Augmented Lagrangian, other modifications. And this is the table regarding each variant of WCA and the problem they solved, the result they found. Actually, the font is very small. And 52% regarding to the other modification of WCA, and the like 22% regarding the chaotic based water cycle. And you can see the figures are very clear, so sometimes no need to explain about the figures. And this is based on the application of water cycle for unconstrained optimization problems. As you can see here, so this is the optimization benchmark in 2016-17. Actually, most of them are not, but I'm not the author of these, even one single paper, because I'm not the author of these papers. None of them is for me. Actually, after 2016, my papers regarding the water cycle, the last paper in water cycle was 2016 or 17. Until now, 3 years, I didn't publish any papers regarding to the water cycle. So this is for constraint optimization problems. You can see the standard WCA for the constraint optimization problem in different fields, in various fields. You can see here, and here for again constraint optimization problem until 2020. You can see they have many papers for the constraint optimization problem, and then here is a comparison between the unconstrained and constrained versions. So you can see that so far WCA mostly applied for the constrained version. So that's okay, because most of the real life problems are constrained problems. So it's logical, and it's a good thing also. You cannot, worry about it. So, but you can also apply, solve more unconstrained optimization problem. And this is related to the multi-objective version of water cycle. We have some hybridization here. So if I'm not mistaken, some of this one is like a modified version of water cycle algorithms, and some of them are a standard version of water cycle algorithm. But for the hybridization, still I didn't see any paper who works with water cycle and other hybrid optimization algorithms. So those are standard version, except this, which is a modified version of water cycle algorithm. Then this is the hybridizations. That one is got multi-objective version. This is the hybridization, like with our artificial B colony genetic algorithms, PSO. PSO is not here. So it's not here. Evolutionary gain, something like that. So with meta-heuristic, it's like this. With other methods like water, wavelet, neural network, massive WCA, with evolutionary gain, something like that, you can see the hybridization of WCA with other optimization method.
Hello?
And this is the application. In terms of the application,
Hello?
classified to the electrical engineering, mechanical engineering, civil engineering, computer engineering. So as you can see in the mechanical engineering, and this is only one of my paper. Usually the scholars are not into the optimization. Usually in mechanical engineering, they are not still into the AI. So that's why I also searched a review for Harmony Search. I noticed that mechanical engineering is still very far from the AI. So that's why we can see less papers from this major. And this is for electrical engineering. There are lots of paper for 2019-18, and control engineering, optimization meta-heuristic, in industrial engineering, mathematics also. This is in terms of the majors, you can 39% belong to the electrical engineering, and the second rank is 17% for, I think,
मेल में सारे हैं,
optimization
WhatsApp
and
में एक दो
meta-heuristic.
मिसिंग हो सकते हैं,
This is
क्योंकि कई लोग अपना WhatsApp
based on the
अपना on
percentage
नहीं
of
रखते हैं.
contributions in different field of study. And you can see again here the number of papers in electrical engineering, around 40 papers. And after that, optimization meta-heuristic 17, and mechanical engineering 1. And this is all the standard version, multi-objective hybridization and modification at the same figure, in the one figure at the same time. We can see the statistics of all the majors. And here shows that in Asia we have more contributions in the field of water cycle algorithm in this optimization method. So we hope in other continents we can have more contribution and collaboration with other scholars. And this diagram is very good point. This diagram shows the categorizing of each optimization method in the specific field. For example, genetic algorithm is the nature-inspired, evolutionary algorithm, population-based, and meta-heuristic. So, for example, Harmony Search is a memory, is a direct optimization method, and in a memory, actually it should be memory population meta-heuristic. No memory. Harmony Search has a memory. It should not be here. It should not be here. It's a no memory. Yes, it should not be here. And for example, where is the simulated annealing? Simulated annealing. Here. Simulated annealing is the trajectory optimization method can be served as a population-based optimization algorithm, simulated annealing, like with multiple points, and is no memory and is still meta-heuristics. So it's a kind of category. WCA is here. WCA can be located in this area as a population-based, naturally inspired, meta-heuristic, and as a kind of implicit version, like PSO, okay, which is here. And kind of conclusion. So I think already we mentioned about the conclusion. We talked about the coding and strategies. So I think we can skip here, and I think we can skip these as well. And if the future directions, we can have more contribution in water cycle in terms of the hybridization and multi-objective version of water cycle algorithms, and also in other majors such as mechanical engineering, we can have more contributions. And also we can use some adaptive and how can I say, most recent improvement version of other optimizers into the WCA to improve the quality and performance of water cycle algorithm. So I think those are enough, and this is our selected references for the WCA. And I think we don't have time for neural network algorithm, I think. Yes?
Yeah, Dr. Ali, I wish we could have NNA as well. But I'm sure we'll invite you again, and you can explain NNA as well. And let me tell you to the participants as well, Dr. Ali has not only founded WCA, he has the founding member and actually the sole founder of many other nature inspired algorithms such as global mind blast algorithm, the one which we are supposed to talk today, neural network algorithm, and I'm happy that I was also the part of that work. So thank you, Dr. Ali, for nice explanation of WCA, along with their MATLAB coding implementation, and sharing the links where the participants can actually go and download, and they can have the hands-on experience on their own. And definitely this flawless presentation and explanation has let many things in the minds of participants, and I hope everyone has enjoyed. Again, we are thankful to you for your time and this nice presentation, and definitely we would like to have you again to address this NNA and other algorithms which you have founded. If you have any questions, then it can be posted here. I had a question that hope we could have had NNA in short. Actually, this question is from Muhammad Karimullah. Mr. Muhammad, I hope we had, but definitely don't feel disappointed. We'll again have Dr. Ali, and he is going to explain NNA in the same way, the way he has explained WCA along with the codes. So I hope it will serve the purpose.
I think we can, in during this period, we can find out one more time slot for Dr. Ali to for explaining of this NNA, and meanwhile other lectures were going on. Participants will be informed for listening time slot, provided that time to Dr. Ali also.
Okay, let me talk with Dr. Ali on this. Then I'll update with the participants. And for the participants, thank you for all of your kind presence here. And I saw the average number of participation throughout the presentation was significantly high, and I hope it will continue to the rest of the series as well. And we'll be sharing you tomorrow again the Google Meet link where we can connect us again. And tomorrow we are going to have another professor which is from Korea, and he will talk again about some other nature inspired algorithms. So hope it was an informative session. So I'm hanging it out now. Dr. Bansal, if you want to say anything, or we can call it a day.
Nothing special. Just if participants have any question regarding this lecture or related to other queries, they can put in the WhatsApp group or mail to Dr. Anupam. And if there is any question which can be answered, which is required the answer from Dr. Ali, then we can coordinate. He can share the answer on WhatsApp or on email also. So, and for all material related query, I have already on the WhatsApp group, I have posted the link of Dr. Ali's web page. So you can go through there, download the slides and all. From tomorrow, we will try to record all the lectures from the beginning to end and all the discussions, so that you can get have the look over those video recordings in later stage also. For that, for sharing of those video lectures, actually we need the permission from all the present participants in writing. Only then we will be able to share the recordings with other participants, because this is a recording of all the participants, and that's why it may take time in getting the consent of all the participants. Only then we will be able to share the recordings. And thank you all participants for the patience listening. It's already 20 minutes more. Still the people are there. Thank you so much. Thank you all.
Thank you all.
Thank you very much.
Just to yes,
I want
Ali,
to give a small comment. Actually, I was thinking to introduce both the WCA and neural network algorithm, but I was thinking in the middle. So if I want to go through for NNA, I don't have much time to describe the WCA in details. Then in meantime, I was thinking, okay, just it's better to finish and complete WCA in more details rather than to just skip the materials and then start a new subject. So that's why I was focusing mostly on water cycle algorithm. And for sure, if there is a chance for future sessions, I will be happy to present the NNA as well. And thank you very much for giving me a chance to present my lecture. And thank you, Dr. Bansal, Dr. Anupam, and Professor Dusum Kip, for giving me this chance to again see you and talk with you, and hope meeting you in Iran or other countries. And thank you very much.
Definitely, Dr. Ali, and really your lecture was very impressive, very interactive, and I can see the comments from in the chat section that the people are really appreciating the lecture, and hope to have the similar kind of lectures in further also. You set a benchmark now. Thank you so much.
Thank you very much.
Thank
You're
you.
very nice. Nice
Thank you,
of you.
Dr. Ali.
Thank
So
you.
tomorrow we'll have Dr. Ram Mohan. He's a professor in Kyungpook University, South Korea, and he will talk about the ensemble learning in evolutionary algorithms. So stay tight, and we'll connect you again. Thank you. Thank you all.